Okay, sequence. I don't like to think about freak out. Sequences. Okay, a sequence is very easy. You just have to basically have a sequence of numbers. Right, and it fits a pattern of some kind. Okay. This happens to be a geometric sequence because we multiply by, what are we multiplying by? Yeah, 1 over 2, right? So this is a geometric sequence. In the general term, it's noted like this. We'll want to make sure that we say that n is the positive integers, or n is greater than or equal to 1, or we can write it like that. Okay. The nice thing about series and sequences is this n is always integer or natural number. So it can be 0, 1, 2, 3, 4, or 1, 2, 3, 4. It's never a decimal, right? So we don't have to worry about that. It's just a term number. So term 1 is 1 over 1, right? Term 2, 1 over 2. You see how those are built? It's basically how you build a sequence. Okay. Make sense? And these can get really nasty.
All right, so like
okay.
A with like the term 3.
A sub,
yeah.
Subscript, yeah, A sub 3.
What,
oh, well.
How does that connect?
Okay.
I mean, because you've got the 1 over
yeah.
1.
This should be
1 over
2 to the n, sorry. Right? And n should start at 0. Okay, that was a good catch. Because 2 to the 0 is 1. 2 to the 1. Goodness, you'd think I'd never taught this before. And then a sub 2 is 1 over 2 to this 2, right? 1 over 4. Okay, yeah. And 2 cubed is 8, etc. Okay, yeah, good catch. So, okay, basic sequence. One thing you'll want to know this is an alternating sequence because that term there, we've talked about alternating, right? When we did Taylor polynomials, we could have alternating Taylor polynomials. We can define n as greater than or equal to 1. So, and then a sub 2 would be -1 squared times 2, which is 2. And you'll see that the positive negative sign alternates. Okay, that will be a key idea for you to get a hold of. Okay.
So anytime it's alternating, just multiply it by -1 to the n.
Yeah. -1 to the n, sometimes it's -1 to the n plus 1. Like if I had -1 to the n plus 1, it would change this to a positive, that to a negative. It would change the sign on the different numbers.
Would you ever have one that alternates after every 2?
I don't ever remember working with one. I'd have to think long and hard about how to make that happen.
Yeah.
So we can bet on the fact that we won't.
Probably not, but you're going to be given these, right? So if there is a formula that generates that, not a big deal. Okay.
Yeah, generate.
You're probably gonna have to generate a few of these. You know, but they're not real difficult. And if it is an alternating sequence or series, it's -1 to the n or n plus 1. Sometimes they'll throw a -1 to the 2n plus 1 in there. Okay. Just changes things a little bit. But. All right. Okay. Let's talk about convergence. Okay, if I were to say one of these two sequences converges, which one would get your vote?
Geometric.
They're both geometric, actually.
Maybe that first one, the general one,
This one? Why?
because it's getting closer to the
Yeah, that's exactly what it is. So this one converges. That's an eraser. Okay. And then to show that mathematically, you're taking a limit at infinity of the sequence. Okay, what's the limit as n approaches infinity of 1 over n? 0, right? Converges. Okay. This diverges, or does not converge. Sometimes we use the language does not converge. Okay, because the limit as n approaches infinity of n goes to infinity. Okay. Right. If you graph this, you can graph sequences, term 1, term 2, term 3, etc., right? So we'd have -1, +2, -3, +4. You see how it bounces up and down? Okay. Let's look at one that does that. That does not converge, but it doesn't go to infinity either. Can you think of a function that does not converge that might go to infinity? Yeah, that's exactly what it is. Okay. Sine of n could be your sequence, and we'll define n as so what are our terms here? What's sine at pi over 2? I don't know if that's great notation on my part, but we'll go with it. Sine at pi over 2 is 1. Sine at 3 pi over 2, you know what? We better do this, because that's not very good notation. I said that was an integer, so let's go pi over 2n and make those integers. Yeah, think that one through. So the first term is sine pi over 2, right? Which is 1. Okay, what's the second term? Sine of pi, which is 0. Third term, sine 3 pi over 2 is -1. Right, so you see that if we graph this, it's just going to keep going, right? Does that approach infinity ever? No, it doesn't, but it diverges. Okay, or does not converge. So that's a possibility too. It doesn't absolutely have to be infinity for a sequence to diverge. Okay.
Now we need to show that the cycles are
Like basically, you're looking at the limit as n approaches infinity of a sub n does not equal a number. Okay, so this doesn't have, this does not exist, right? That's how we would answer that. Right, so we would say this sequence diverges. Yeah. Let's see here. How about the sequence? Converge or diverge? What's the limit as n approaches infinity? How do we tackle infinite limits?
Use the
Highest exponents, it gives us 1. Okay, so this converges. It just doesn't converge to 0. It goes to 1. Okay, so if you get a number here, you're good to go.
Oh, so you just go to any number?
Yeah. Yep. Doesn't have to go to 0 for a sequence. Okay. So sequence, if it converges to a number, you're good. You ever heard of how many of you have been in computer science? 2, 3, or 4. You know what a recursive sequence is?
Yeah.
You know what recursion is, right? So one term and then the next term uses that to calculate itself. Okay, so here's an example of a recursive sequence. Yeah. Let me write that better. And you're going to define the first term as a number. Right, so we have a value for term 1, right? What's term 2? Right? And this is going to be what number? 1, right? This is a sub 1, so we just take a sub 1, put it in those 2 spots. So 1/2 1 plus 2 over 1, which is 3 over 2, right?
Wait, so A of 2 is just equivalent to plugging in A of 1 into your equation?
Yeah. So a recursive sequence uses the prior term, maybe the prior 2 terms.
So then for the next one, you would just use that same function, except you plug in 3 over 2 instead?
Yeah. Yeah. So 1/2 3 over 2 plus 2 3 over 2. That's your next term, right? Can anybody think of a very famous recursive sequence?
Pi.
There you go. Say it louder.
Fibonacci sequence.
Fibonacci. What's the recursion there?
So 1, 1, 1, 2, 1.
Yeah. So
I'm very happy that I have a
1. Okay. What's the third term?
1, 2, 1.
2. Right? Because you add these 2. What's the next one? Add the prior 2. What's the next one? 5. And then we add these and get 8. Right? Right. Very Most famous one of all.
That one's not very complicated.
No, it's not very complicated at all, but
What's it used for? To demonstrate recursion.
making people go, ooh, and ah.
That's it.
I know. Dan Brown made a lot of money off of that one right there. The Da Vinci Code. Right? It's just interesting, famous sequence. Okay.
Da Vinci Code. That's pretty good.
I think let's do one or two more. I think we'll be good for today. Okay. A little bit more difficult to determine convergence or divergence on this one. So if I just quote plug infinity in, what do I get for the top and bottoms? What's the top go to? Infinity, right? Because if you put infinity plus infinity in, you got, it goes really big, and then the bottom's going to go to that as well, right? So what would you think to do next on that limit? Because you have an indeterminate form. L'Hopital's rule. Yeah, yep, that's exactly what it is. So your limits still exist, and you can still use the same solution methods as before. Right, so what do we get? 1 plus 1 over n. Right. What does that go to? 0? Yeah, so this
How does it go to 0?
okay, this is 0, right? Because you have 1 over infinity. And then, so you have 1 plus 0
Over infinity.
over infinity, basically, yeah. So, it gets really big on the bottom, not on the top.
How does 1 over infinity make 0?
It's infinitely getting smaller. Smaller and smaller.
Oh, yeah, that makes sense.
Right, so 1 over 100, 1 over 1,000, 1 over 10,000, getting closer to 0, right? Yeah. Okay. Do you know what a Balmer wavelength is? Any physicists in here?
Thankfully not.
No? I will spare you then. Sound good?
Yep.
Let me make sure that I cover everything for
I
the day.
think the physics thing we gotta learn about.
It's about light.
I think we're getting to that table.
Fantastic.
So I think the computer will.
She's gonna give us our
start
music
talking about
project this year.
variables.
I'm not happy about it.
Instrument, build an instrument.
Yeah.
That's an eraser. Seems to be a theme today. Too bad I didn't write it first and then erase it, right? Ooh, that's not it. Okay, so this is there you go.
That's for response 1, right?
Yeah. We will check this on Thursday. So if you want to get started, you can tonight, today and tonight, because you
Is there anything
You
we
got-
can't do right now?
on this assignment
Yeah.
can always read your book. I
would we do
would.
that?
Let's see. Prelims. If you want to write down what I have taught you. Prelim 1, 2, prelim 3, 4. Okay, so prelims 1 through 4 are definitely possible. Exercises. 1, 3, 6, 17, 26, 63, and 64. Those are all definite. So you can pretty much do all of it.
So you just can do one.
There's just a prelim that you'll have, yeah, tomorrow will be a little bit more theory based.